Okay, hi everyone. This is second lecture on continuous random variables. This will talk about the topics you see here, the cumulative distribution function, which also applies to discrete random variables, but you don't really need it for them. And you do really need it for the continuous ones. So we've waited to now to introduce this. So we're going to start with this and then get into a function of a continuous random variable. If I have a continuous random variable, CRV, for which I know the density, I take a function of that random variable, like I square it or take the sign of it or something. Well, that should also be just a function of something continuous. It's also continuous random variable, and we want to consider those. And we want to consider maybe how to find probabilities and expectations of those. So that's the whole lecture, this one that's October 25th, now being recorded for you who couldn't make it on the 27th. And then next week, we will have 2 lectures on the normal random variable. Okay, and that will take us through the second third of the course. Okay, so the cumulative distribution function. Okay, so we define, so say the definition. Okay, say X has PDF density function f of X, then we have f of X, capital F. You put a subscript there, like a capital X, to refer to the random variable if you need to distinguish it from maybe other CDFs. But if you really want to be clear, write what it means. Probability, the random variable is less than the number little x. And this is just equal then to the integral up to little x. And I need a different letter here for the dummy argument to the integral. Okay, it is called the CDF. Of course, I'm trying to save writing, so I'm going to just use abbreviations and say it. You can hit pause if you need to slow down and write it out. 4x of x or 4x. Now capital, right? Okay, right. So it just accumulates the probability that x is less than or equal to some number. And this does away with a lot of the some of the problems that can happen with densities where you're dealing with the real numbers. Okay, so let's do a quick example, computing one. So for example, say I have x, say uniform 0, 1. Then the CDF and probability x is less than x. This is the CDF is equal to, okay, so remember the PDF looks like this. It's just a square here, right? This is little f of x, PDF. And the probability that x is less than or equal to any x. So this is a function, and you want to map the probability that's accumulated up until little x. So you can see there's 3 places where it's going to, you got to treat it sort of separately here. So it's going to be 0 if x is less than or equal to little 0. It's going to be little x if x is between 0 and 1. And it's going to be 1 if x is greater than 1. You notice that it is continuous at the points here, at the piecewise points 0 and 1. It's not differentiable at those points, but it is continuous at those points. If I sketch it, then the CDF just looks like this. It's 0 up to here, and then it goes up to 1 here. It goes like this here. So this is the CDF. Okay, that's the CDF for a uniform 0, 1. If I'm interested, say, in the probability that capital X is less than 1/2, I just see what the value of the CDF is. Okay, so at 1/2, I go here, it's 1/2. Of course, if you just need the probability at a particular point, you don't really need to find the whole function of the CDF. You can just integrate at that particular point. But sometimes it's useful, as we'll see in a second, to have a CDF function. Let's look at another example before we get more general about this. So example 2, say X is exponential with rate lambda. Okay, so then the CDF probability X less than or equal to little x. Quick way to do this is just to use the complement. This is 1 minus the probability X is greater than little x. And this we saw last time is e to the minus lambda x. 1 minus e to the minus lambda little x. Okay. Okay, so we did this last time, so I don't need to repeat that again. So if you want to see what this looks like, we can graph this. It's like this, it's 0. Oh yeah, I forgot to do this. So this is equal to this for x greater than 0, greater than or equal to 0 if you like, and probability x less than or equal to x equals 0, or x less than or equal to 0. So it's like this here. It's continuous, but not differentiable here. There is this corner here, and then it takes off like this toward 1 here. Right? As x gets big, this goes to 0. The whole thing goes to 1. Yeah, let me see. Right here. This will go to 0. As x goes to infinity, the whole thing goes to 1. As x goes to positive infinity, and that's for x greater than 0. Okay, let's see. Yes. So you can find these, how to sketch these by using a graphing calculator, but of course, it's this one, not too hard to do. You can sort of think of it in a couple steps if you like. Let me just do this just to get it out of my system, because if I don't, I will. So what I always remember is if I have a decaying exponential like e to the minus lambda x, this would look like this. And then if you want minus e to the minus lambda x, right, it's just the mirror of this, minus e to the minus lambda x. And then this would be minus 1 here, right, and plus 1. And then if I add 1 to this, it just starts at 0 instead of -1 and goes like this. Instead of approaching 0 here, it is approaching positive 1. Okay, so this is the probability. X is less than x. Okay, let's now take on the functions of continuous random variables. All right, so yes, okay, so here's the question. So we're already on 2. Okay, this is going to go fast because I think this is enough given the book and the homework that you can just refer here to see basically what you missed, but there's no questions incoming, and I'm not going to elaborate much. I don't want to write much on the iPad for reasons I explained. So let's go on. We're on to number 2 already. So let's say functions of continuous random variables. Okay, so let's do an example. So let me just let you know that we're here now. Functions of CRVs. Okay, let's look at an example first. And I'll look at a couple things. So example, suppose X is uniform 0, 1, and we want to consider a function of this, and y, say, is equal to e to the x, e to the capital X. Then y is also a CRV. Shouldn't be hard to realize that because I just have a function x that satisfies I have a random variable x, satisfies the axioms of probability, it's continuous random variable, and now I just map that under this function to y, so y is also random, and it is also a continuous random variable. We can verify all this now, but I feel that it's sort of natural. Okay. If not, we can follow up. I don't want to okay, I'm starting to talk to myself a little too much. So we have y is equal to e to the capital X. So couple questions. So let's ask a couple questions. A, find, say, the probability that say y is greater than, I don't know, 2. Okay, how to do this? Well, I think, see, y is e to the capital X, right? And I understand the distribution of X completely. It's uniform 0, 1. So maybe I can answer it that way. So solution, probability y greater than 2 is just equal to the probability e to the x is greater than 2. That's a sensible probabilistic statement. That second one, right? There's a random element in it. And I didn't do anything. Y is e to the x, right? Next one, I take the log of both sides, and the inequality maintains its direction because it is an increasing function, the log. So I have this is equal to the probability that x is greater than log of 2, which is some number around 0.69. And I know the distribution of x, right? So this is just equal to 1 minus log of 2. Okay, log of 2 is between 0 and 1. It's about 0.69. So this is approximately, I think, unless I'm forgetting, 0.30 something. 3. I don't remember. Okay, does it not? You get it, right? This is the probability that y is greater than 2. All right. All right. This is how you do this, okay? You can make these substitutions, and then hopefully the function is not so complicated that you can't solve it. But if it is, you have to solve it maybe numerically or something like that. Okay, this is, I don't need to know the density function of y to solve this particular example, part A. But say I do want the density of y for some reason, like I want to do more with y, and I would like to know the density. Then what do I do? So let's say B, find PDF of y. Well, I can't go directly from the PDF of x to the PDF of y, I guess is the point. So that won't be possible. So I have to use the CDF. Okay, so solution, and I didn't write this above, but it's worth noting, we can note it now. Use CDF. So I'm going to write a few notes here. Okay, so one fact is about the CDF is, note the derivative of the CDF is the PDF. D little y, probability y less than little y. is equal to the PDF of y, is equal to f. I'm going to use the subscript because, as we talked before, if we have two variables, it can be confusing. So I'm going to use this means the PDF with respect to the random variable y, as opposed to the PDF with respect to x. Okay, why is this true? Let's see. Let's prove this. Proof. Okay. D little y, P y less than little y is just equal to d little y integral minus infinity to little y. And now I need the PDF of y. I need a dummy variable, dt. Right, and this is equal to, what is this? Fundamental theorem of calculus, right? This is equal to f y little y. This is called the fundamental theorem of calculus. So if I have some function and I have a function that is accumulating the area here, so that's this kind of function here on the outside here, it's accumulating the area here, then the derivative of this is the height of the function here. The rate of change, right? Makes sense. If it's a higher function, then the area is going to be increasing faster. If it's 0 at this moment, there's no net increase, instantaneous increase in the area. If it's negative, it's increasing negatively. Okay, so the derivative of this is represented by the height. Really just a big statement that says the derivative and the integral are inverses. So, okay, right? So I can use, if I know the CDF of y, I can get the PDF of y. So I can go from the CDF of x to the CDF of y in the way I sort of did this here, right? CDF of y at a one particular value. And I turned it into CDF of x here. So we're going to do that just in the general case to get the answer, okay? All right, so back to our problem. All right, so we have y equals, okay, so we have, let's summarize. This is like a little result inside an example. We have probability y less than or equal to little y. The CDF of y is equal to, well, it's e to the x, right? E to the x. This is equal to the probability e to the x is less than or equal to little y. Okay? And this is equal to a couple things, right? So this is equal to, what is the range of e to the x? What is the range of this? Well, x goes from 0 to 1. So this is, and this is e to the x is increasing. So at minimum, it's 1. At maximum, it's e, right? So if x can't be less than 0, so this can't be less than 1. So let's do it like this. If y is less than 1, this probability is 0. Okay, for little y less than or equal to 1. And if y is greater than or equal to e, it's 1. This is always less than or equal to e. Now, what about in the middle? What about in the middle? Well, in the middle, this whole thing, maybe I can write it here and then we'll just fill it in here. This would be equal to the probability x is less than or equal to ln y, which is ln y. And this is only for the middle though, right? For for y between 1 and e here. Okay, so this is ln y. Okay, so you see it's continuous, it connects there. And yeah, if I put 1 in here, right, it's 0. And if I put in e in here, it's 1. So, so this is the PDF, the CDF of y, the CDF of y. Well, let's draw it just for the hell of it. I don't think I did this in the lecture, but let's just draw this. What does the CDF of y look like? E to the x. It's 0 all the way to 1. And then it's ln y. So it sort of looks like the other function. It's slowly increasing from 1 until it gets to e. It's just the natural log function to e. And then it's at 1 here. And then it's just straight over like this. Okay, so this is probability y less than little y. Okay, so for the PDF, right? PDF, I just take the derivative. So using the fact above, the PDF of y, e to the x, where x is uniform 0, 1, is just equal to the derivative of this. And this is kind of fun. You can just, taking the derivative is easier, and you can just take the derivative of each one in turn. The derivative of 0 is 0. The derivative of 1 is 0. So this is piecewise, but only for 2 things. So it's 0 else. And the derivative of ln y is 1 over y here, right? Okay, and this would be for y between 1 and e. Yes. Yes, that's fine. So 1 less than or equal to y less than or equal to e. Okay, so the density is decreasing here. So it's going from 1 over 1. This is just the 1 over y function, the hyperbola, down to 1 over e here. And 0 over here. Doesn't really matter where you want to put whether you want to include the endpoints or not, it doesn't matter. This is not continuous, as you notice. There is this jump here, that's fine, okay? Just at those 2 points, and that's fine. And it doesn't matter where you want to put the points for this function. Okay, so this is fy of y. Okay, all right. Well, we could verify this integrates to 1. Let's just do it in our heads. The antiderivative of 1 over y is ln of y. If I evaluate between e and 1, I get ln of e minus ln of 1. 1 minus 0 is 1. Okay, so it integrates to 1. It's positive. It looks right. But you notice we didn't need to find the PDF to answer the first question. So that's one of the things I wanted to make clear. Don't need to always find the PDF, but it is important to know how to find the PDF. Okay, let's see. Yes, all right, so we're getting there. So we're on 3, I think now. I think we can go to the next and last thing. I don't think there's any reason to stay on here longer than needed. These videos are not necessarily that fun. And so let's just go back to the lecture. Comments are suspended. Okay, so the last thing, how do I find the expectation of a function of a continuous random variable? There are definitely 2 ways to do this, just like for the discrete random variables. And we're not going to focus, I don't think, as much on the proof of this or at all. And just sort of write down the fact this year so we can move on. So expected value of function of CRV. Okay, so suppose X is a CRV with PDF f of X. So let X be with density maybe we should put a capital X there to make it clear, okay? Subscript with the capital X representing the random variable, right? The random variable has to have an associated distribution, associated PDF. So that defines everything about what you're doing now. So there's two ways. The two ways to find E G of X. One is by the definition, which we're not going to linger on too much. So we let Y equal G of X, find the density of Y using the method above, and then E G X equals E of Y equals integral minus infinity, infinity, little y, Fy, y dy. Okay, two, this is a derived fact that can be proved, and I have in fact proven this in this course before, but I'm not going to this time. It is in the book as a problem. Second way is just to use a fact, and this is completely analogous to the one that we did prove for discrete random variables. So the second way is just use this fact. Used fact. E is equal to the integral minus infinity to infinity G little x f x x dx. In other words, I am looking here and running across X, looking at the density, and instead of weighting just the identity function, just X, I just weight G of X. Very natural, very analogous to the discrete case. Okay, we're going to use two, I think, exclusively, unless we have the density lying around, then we might use one. Example. Find E X squared for X uniform 0, 1. Okay, we're using 2. EX squared equals integral minus infinity, infinity, little x squared f of x dx equals. This is 0 everywhere except between 0 and 1, where it's 1. So antiderivative of x squared is x cubed over 3. So we get a third here. Okay, so Well, the expected value of x, uniform 0, 1 is a half. The expected value of x squared is a third, right? When I square a number between 0 and 1, it makes it smaller. So it makes sense that the expected value of x squared is less than the expected value of x. And indeed, we have just shown using the fact that we do get something left. Now, I could find the PDF and do it that way again. I'm going to skip this to save writing and make the video. It will make the video a little shorter. So let me just put it as an exercise or an LFS, I think, left for student. Use 1 to find same. Okay, so find the PDF of x squared when x is uniform, and then use that PDF to, so let y equal x squared, find the PDF of y, and then find the expected value of y. Okay, what about the variance? Now we can, so one reason we want this, but not the only reason, is to compute variances. So now we have the variance of x, the uniform 0, 1, is equal to e x squared minus e x squared, which is equal to 1/3 we just found, minus 1/2 squared equals 1/12. Yes. Okay. All right. Yeah. Okay. You can get the standard deviation from that by taking the square root. Okay, let's do a second example. I'm going to use the fact again. Example 2. Let's do the same thing. Suppose x is exponential lambda. Find the variance, or we already know the mean. Let's find the variance. So find ex squared. All right, I'm going to pause just to rest my hand for a second, and then okay, I took about a 20-second break. Not much more to go. So if you're doing this so that you make sure you don't miss anything, it's good. But this is short. You see how much faster it goes when I'm just talking to myself here. Okay. Yeah, so let's do this now. So we need e of x squared, right? So let's use the property. We're going to basically use the property whenever we can. So ex squared equals integral minus infinity, infinity, little x squared, lambda e to the minus lambda x dx. Let u equal lambda x, so that du equals lambda dx. And lambda's positive, the bounds stay the same, so we have e x squared equals same bounds. Sorry, the lower bound is wrong here. I just wrote that. I meant to write f of x here. So this would be right if this were f of x. Let me just put that in so I don't confuse you, because now I feel like I've made it confusing. So it's x squared f of x. That's why I put it in originally. I just wanted to show there was nothing new going on here. Okay, x squared f of x. This is the PDF dx. But this is equal to, we know the PDF is 0 for negatives, but for positives, it's x squared lambda e to the minus lambda x dx. Okay, we're back. Okay. All right, so we have that, and we're going to make this u substitution. So I see x is u over lambda. So we get integral 0 infinity still, lambda's positive. I have u over lambda squared. And I have this lambda goes with this dx, so I get e to the minus u du. So cleaning this up, I have 1 over lambda squared, integral 0 infinity u squared e to the minus u du. This is one of those functions we talked about before. This is a gamma function at an integer and is equal to, when you see it in this form, we claimed before that this kind of thing, when n is a positive or non-negative integer, it's a gamma function, but we're going to go into that a little later. But if you see this form where n is 1, 2, 3, 4, 0, 1, 2, 3, 4, etc., this is just equal to n factorial. Okay, so you should just know this. So this is 2 over lambda squared. You prove this by integration by parts and a pretty easy inductive argument from that. We'll do it. We're going to do it in class. I don't want to do it now. We don't need to do it. You can convince yourself or look it up. Okay, so we have then finally the variance of an exponential then is just equal to ex squared 2 over lambda squared minus ex all squared. That was the expected value, remember, was 1 over lambda. I square this, so I get 1 over lambda squared for the variance. You notice the standard deviation, the positive square root of the variance is 1 over lambda, which is the same as the expected value. If I draw the PDF here for, say, something, probably not a very good picture, but say I have some PDF, here is lambda here. Maybe the expected value here is 1 over lambda. So maybe I'm thinking of this as like 3 1/3 here. Then the standard deviation, it goes down to 0, right? Something like this. And I get standard deviation to the left and the right of the mean. Okay. And the variance is 1 over lambda squared. Okay, so this is lambda e to the minus lambda x. All right, these are just definitions. So remember this idea that with the exponential, when the rate is high, the mean is low, right? So let's put a couple values in here. So let's say we have like some low one. And so let's call this, maybe this is 4 and this is a quarter here. And some high one, maybe this is 3 or something, and decays really sharply, and say the mean here is 1/3. So this would be E X, say this is now E Y or something. This is a 4. Okay, so these are just two different exponentials. I don't want to write much with different lambdas, right? So this is lambda equals 3, lambda equals 4. And just the point is that when the rate is, lambda equals 1/4. When the rate is low, that means the events are occurring more slowly, the rate is low, and the mean is bigger. The time until the next event is longer, so the mean is bigger. And when the rate is high, bigger than 1, well, then the mean is lower. So a big number, the reciprocal is a small number. Rate is fast, so the time until the next event is low. And you see the variance also plays into this too. So with a slow rate, I get a big mean, and I also get a bigger variance, right? Like the variance here is 16, and the standard deviation is 4. So it's more spread out, and there's more variation. With a higher rate, everything's compressed. Time until the next event is soon. Less variation. The variation's even more constrained. The variance of this is 1/9. Okay, so for this x, the variance of this x, is equal to 1/9. The standard deviation is 1/3. Everything's more compressed. All right, that's going to do it for this. We start the normal random variable next time, and not too much theory until the second lecture on the normal random variable. We'll be talking about the famous central limit theorem. First one's just basics on the normal random variable, and that's going to do it for this lecture. Thank you very much. Adios.